On November 21st, Super Heavy Booster 18, the first next-generation Block 3 Super Heavy, experienced a catastrophic structural failure during ground testing at the Massey's outpost. Planned to fly alongside Ship 39 for Starship Flight 12, the vehicle suffered an energetic rupture at the very start of its proof campaign. The incident immediately ended Booster 18's qualification timeline and pushed Flight 12 several months past SpaceX's original target. To understand what occurred, we need to go frame by frame and analyze what the event confirms and what it rules out. The fully stacked Booster 18, carrying a long list of Block 3 enhancements, rolled out to Massey's early Thursday to begin its pre-launch testing program. The goal was to validate the redesigned propellant systems and evaluate structural strength under pressurization loads. After reaching the stand, the vehicle was instrumented, hooked up, and prepared for cryogenic readiness operations. Early Friday morning, venting began around the tank farm. At this stage of the campaign, the booster was undergoing an ambient pressure check prior to any cryogenic loading. Ambient pressure testing is a standard qualification step in which the tanks and associated plumbing are pressurized at normal temperatures using inert gases, typically gaseous nitrogen. The goal is to verify structural integrity, confirm leak tightness, validate plumbing paths, and ensure venting systems function properly before moving into the far more demanding cryogenic proof phase. Minutes after the test began, the anomaly struck. A violent rupture tore open the lower liquid oxygen tank, peeling a large longitudinal section outward like a tin can and releasing gas from the lower region. The booster remained upright, and the methane tank above stayed fully supported. Slow-motion review indicates a sudden internal overpressure or rapid pressure imbalance that exceeded the structural margin of the oxygen tank wall. SpaceX later issued a statement acknowledging the anomaly, confirming that the booster failed during a gas system pressure test conducted before structural proofing. They emphasized that no propellants were loaded, no engines were installed, and all personnel were safely positioned, preventing injuries. The company noted that engineering teams now require time to investigate before determining the root cause. Although the root cause remains unknown, multiple credible explanations exist, with several standing out as more probable. Because this was the first Block 3 Super Heavy, Booster 18 featured major upgrades. These included a new integrated hot stage ring, a reinforced forward dome engineered for more violent stage separation forces, larger grid fins, redesigned aft plumbing, and a new methane downcomer. As soon as the rupture became visible, attention naturally shifted to the transfer tube, which runs through the affected region. Elon Musk previously confirmed that this tube is not just a feed line, but part of a header tank integrated system storing propellant for return-to-launch site maneuvers. He also noted it experiences extreme loads and that even a small leak would be game over. However, the transfer tube was not the cause of this failure. The tube was neither filled with cryogenic propellant nor subjected to flight-level loads this early in the campaign. It would have been at ambient conditions, likely carrying only gaseous nitrogen for leak checks, which cannot create the extreme pressures required to rupture a structure of that scale. The fact that the methane tank remained fully suspended after the blast is further evidence. The downcomer continued supporting the upper tank's weight, showing the structure stayed intact after the event. A transfer tube failure would almost certainly have caused the upper tank to collapse. With the transfer tube ruled out, the rupture location shifts focus to another critical set of hardware, the composite overwrapped pressure vessels, or COPVs, mounted inside the chines near the aft section. These vessels store helium or nitrogen at high pressure for engine spin start and pneumatic control. COPV failures are rare but extremely energetic. A bursting COPV can tear through stainless steel tank walls. If one suffered a liner crack, resin degradation, or regulator malfunction, it could explode and punch directly into the surrounding LOX tank. A similar COPV failure destroyed Ship 36 in June during a static fire attempt. Fortunately, Booster 18 carried only inert nitrogen and no propellants, preventing the fireball that consumed Ship 36 and sparing the Massey's test site, which is still recovering from that incident. Another strong candidate located near the rupture zone is the autogenous pressurization plumbing. These lines carry hot engine-derived gases back into the tanks during flight to maintain ullage pressure. During proof testing, they are filled with inert nitrogen to validate leak tightness and structural performance. The rupture aligns exactly with the region where these lines run, and because they interface directly with the LOX tank, a failure here would immediately transmit mechanical energy into the tank wall. If an autogenous line or one of its manifolds overpressurized due to a stuck valve, a blocked vent, a misconfigured setup, or a faulty sensor, it could fail violently. Weld fatigue, poor weld penetration, vibration-sensitive joints, or a flaw introduced during the new Block 3 plumbing build could create precisely the outward peeled tank breach seen on Booster 18. A third possibility is a malfunction of the oxygen side quick disconnect. Block 3 debuts a dual BQD configuration with independent methane and oxygen fill points, and Booster 18 was the first vehicle to use the redesigned system. While the new design improves flow efficiency, it also introduces new plumbing runs, additional valves, and expanded sealing surfaces. If the oxygen side connector was even slightly misaligned, if a valve sequenced incorrectly, or if the vent path failed to open, gaseous nitrogen entering through the fill line could raise LOX tank pressure faster than the vent system could manage. At ambient temperature, this type of trapped overpressure creates exactly the clean outward rupture pattern observed on Booster 18. The methane tank remained completely unaffected, suggesting the methane side quick disconnect performed properly. This strongly points toward an oxygen side plumbing or QD-related issue. Another potential, though less likely, source is the new side tank located low inside the LOX tank, likely designed to store supplemental propellant for RTLS maneuvers. If it were pressurized independently, a rupture could transfer loads directly into the surrounding oxygen tank. However, Booster 18's failure tore open a tall vertical section in a single instant. A small internal tank mounted near the bottom cannot produce a failure pattern that propagates far above its installation height. This mismatch makes a side tank failure far less plausible than issues in the autogenous lines, COPVs, or oxygen side fill hardware. Flight 12 had originally been targeted for January, as confirmed by SpaceX Vice President of Launch Kiko DNV. With Booster 18 now lost, that schedule is no longer achievable. SpaceX will conduct a full mishap investigation to pinpoint the failure mode, develop corrective actions, and implement fixes across the fleet. Booster 19, the next vehicle in line, has not yet begun stacking, and will remain paused until engineers identify the root cause and validate the necessary redesign. As a result, Flight 12 will be delayed by several months. This is certainly not the opening to the Block 3 era SpaceX hoped for. The only silver lining is that the failure occurred during early proof testing with no cryogenic propellant on board. Had the same rupture happened during pad-level cryogenic operations, or worse during a static fire at Pad 2, the resulting fireball could have caused major pad damage and pushed Flight 12 deep into next year. Booster 18's failure highlights a critical truth. Proof testing is never routine. When a stage undergoes a major redesign, structural margins shift, load paths change, and new failure modes appear. Block 3 is designed to support higher thrust, more aggressive flight trajectories, and faster reuse. But those improvements move the system into a regime where pressurization dynamics and structural behavior diverge from previous vehicles. The incident reinforces a foundational principle of iterative rocket engineering. Pushing performance exposes weaknesses that only full-scale hardware can reveal. Booster 18 provided data that no simulation could have predicted. The coming months will focus on digesting those lessons, reinforcing the design, and preparing the next booster to avoid the same failure. Flight 12 will launch, but only after the Block 3 architecture proves it can survive its own qualification campaign. Thanks for joining me for this in-depth breakdown of the Booster 18 anomaly. If you found the analysis valuable, hit the like button, drop your thoughts in the comments, and share the video with friends. And don't forget to subscribe and turn on notifications so you never miss an update.